In this videocast, we'll take a look at how to find the equilibrium constant after we've used the electromotive force or the voltage of a cell to find G. After we do that, we'll take a look at finding E, G, and K at non-standard conditions, and also some of the other things you can find at non-standard conditions. And then lastly, we'll take a look at some specialized circumstances when we use E and at non-standard conditions to find some portions of Q, which remember is the reaction quotient. So with that as a start, please make sure that you have this videocast sheet in front of you with the problem that says calculate the free energy change in the equilibrium constant K at 298 for this reaction in front of you. And then make sure you've got a pencil or a pen. It's helpful to have a calculator because then you can follow along and try the calculations yourself as well. Now in the last videocast we finished by finding delta G at standard conditions. Remember this little circle means standard conditions, which is 298 Kelvin. 1 molar solution, 1 atmosphere pressure. There were 4 electrons transferred. That's what the N stands for. F is the Faraday's constant. Remember the units on the Faraday constant are joules per volt times mole. And the E circle, remember, is the electromotive force or the voltage or the potential difference of the cell. Remember that there are about 6 different ways of saying E, but really what it means is look on this sheet right here and find out the E circle or the voltage for the standard reduction potential, and then subtract anode from cathode. We'll do a bunch of that solving too. So once we found G turned out to be 170 kilojoules per mole negative. 170 kilojoules per mole negative. Now find K. And if you remember back from chapter 19, there was a relationship between G and K, where G, and in this case it's G circle, because it's at standard conditions, is equal to negative RT natural log of K. And of course our goal here is to find K. We know G, make sure it's in kilojoules per mole, is negative 170 kilojoules per mole. And then it's equal to negative R, which is 8.31 joules per mole Kelvin, but since this is in kilojoules, we're going to put this in kilojoules as well. Kilojoules per mole Kelvin. Or another way to write the kilojoules per mole times Kelvin. That's the units. And then T is the temperature, which is 298 Kelvin, because we're at standard temperature. And then this is ln of K right here, our natural log of K. We need to solve or get K alone by itself. So we'll divide both sides by these numbers right here. Bringing these over to this side, we have the natural log of K ending up being equal to, once we do all this division, 69. And then to undo the natural log, remember, we do the e to the x key on our calculator, and so e to the 69th power is equal to K, which would be 9 times 10 to the 29th. An incredibly large number. But this is pretty typical of redox reactions, that we have some really large equilibrium constants. It's because they're very one-sided reactions. There's just going to be a lot of products produced. Notice it's a really large positive number, and there's not going to be much reactants left. So notice this is 9 times 10 to the 29th. I'm going to write it on this next page. This was when we had this reaction of 4 silvers plus oxygen plus 4 hydrogens makes 4 silvers ions plus 2 waters. Now, the next question on your next page in your videocast packet takes the same equation, but in this case now we have 2 silvers, 2 hydrogens, and 2 silvers being produced here. It's the same exact equation, except it has half as many moles. And it says find G and K when the reaction is written this way. So I'm going to go step by step through this, and if you want to skip through how to find the EMF of the cell, you're certainly welcome to do so if you know how to do this already. But first thing we need to do is write the half reactions, and you'll notice silver is 0 of a charge here, and it's positive 1 right here, so that's the thing that's oxidized. And in this case, it's 2 silver goes to 2 silver positives plus 2 electrons, and this is our oxidation, which, remember, it's an-ox, so this is our anode right here. And the standard reduction potential for this, if I look it up on the yellow sheet, silver's standard reduction potential is right in here. Silver's is 0.8. And my second half reaction then is going to be this oxygen and hydrogen going to water. And so really what I have here is 1/2 O2 gas plus 2 H pluses goes to H2O over here, and technically I'm getting 2 electrons added to it here as well. And if I look up this standard reduction potential, this one is 1.23 volts. And I can find that on here. Right up here, you can see that it has 1.23 for its electromotive force, and here's my balanced chemical equation right there. You'll notice that on the standard reduction potentials page, they've got a 4 hydrogen, a 4 electrons, and a doubling of the water, and it has an EMF of 1.23. And then if you look on mine, notice it's 2 electrons, a half oxygen, 2 hydrogens, and only 1 water. But notice I still wrote down the same cell potential. This is actually one of the properties of cell potentials, or of electromotive force, is what's called an intensive property of matter, because it's independent of the amount of stuff you have. So therefore, to find the EMF of the cell, remember we do cathode minus anode, so 1.23 minus 0.8 volts. And so when I subtract those two, I end up with a cell potential of 0.43 volts. 0.43 for the cell. That's part 1. Find the E circle at standard conditions. Next, it asks me to find delta G circle. And remember, the equation for this is delta G is equal to negative NFE. And the N here, if I look at the balanced chemical half reactions, are 2 electrons are gained here, and 2 electrons are lost here. So the N for the delta G equation is 2. The F, remember, is Faraday's constant, which can be approximated as 96,500 joules per volt times mole. And then E is the electromotive force, or our standard EMF for the cell, which is 0.43 volts. Multiply those guys together, and I get a delta G of negative 83 kilojoules per mole. Notice I converted it to kilojoules right away after I multiplied those together. It's like 83,000 something, 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 but that's close enough. So there's our delta G. That's part 2. And lastly, it says to find the K, the equilibrium constant for this reaction. And remember, to find K, we can use the delta G is equal to negative RT, natural log of K, just like we did in the last problem. And we're going to solve for K. So we put the delta G in there once again, which was 83 kilojoules per mole. And be careful of your R then. Make sure to use 0.0831 joules per mole times Kelvin. 0.00, sorry, because you want it to be in kilojoules per mole Kelvin, and so you have to move this to kilojoules. And then the temperature, of course, is standard conditions, which is 298 K, and then you have to solve for the natural log of K. And since we did that last problem, I'm not going to do it again. But it turns out that in this case, K, after you move these things to the other side and undo the natural log, is 3.5 times 10 to the 14th. Now, the reason I wrote the K down here and up here is because you'll notice there's a difference between the two. In the first problem that we did, remember the balanced chemical equation was 4 silvers makes 4 silvers and 2 waters with 4 hydrogens. In the second equation, remember that it's 2 silvers, 2 hydrogens, and 2 silver ions over here. Now notice the difference. Notice the difference in the K's for these two reactions. This one was 9 times 10 to the 29th, and this one was 3.5 times 10 to the 14th. You can see that K is what's called an extensive property of matter. In other words, it depends on the amount of stuff you have, whereas E is an intensive property of matter because the overall standard reduction potential for the cell remained the same. G is another extensive property of matter and depends on the amount of stuff you have as well. Two good concepts to keep in mind. Let's look at the next problem. In this one, we move outside the box just a little bit, and we move to a place where we have some conditions that are not standard anymore. We're not at 298 Kelvin anymore. Well, yes, we are, as a matter of fact, but we're not at 1 molar solutions or 1 atmosphere of pressure any longer. And if you look at this, it says calculate the EMF at 298. That's generated by this reaction right here. And as a matter of fact, we did this reaction's standard reduction potential a while ago in this video, well, in a previous video cast. And it says when the concentrations are changed to 2, 1, 1, and 1.1 times 10 to the negative fifth, respectively. Iodine solid and water liquid don't have concentrations, and they're not going to be in equilibrium constant or Q expression. So the equation we use here is what's known as the Nernst equation. And the Nernst equation says that you can calculate the electromotive force, or the voltage, at non-standard conditions by taking the electromotive force at standard conditions and subtracting 0.0592, dividing it by the number of electrons transferred, and multiplying it by the log of Q. Q, remember, is the reaction quotient. Now this is only true at 298 Kelvin. If it's not at 298 Kelvin, then we actually have to make some changes here to adjust for a different temperature as well. Have to make some changes here to adjust for a different temperature as well. And if you look on your crappy periodic table, in the equation sheets here, underneath oxidation, reduction, electrochemistry, let's see if we can get this to focus on here just a little bit. You can see that here is the E of a cell is equal to E cell minus, and then you can see this RT over NF. The F here is the Faraday times the natural log of Q. Now this is the Nernst equation when you don't know what the temperature is. But if the temperature is at 25 degrees Celsius, now the R times T divided by Faraday's constant becomes 0.0592. And that's where this equation comes from right here. You can find this under oxidation, reduction, electrochemistry on your equation sheet. And of course, it'll be available to you on the AP exam as well. So our job in this is to find the EMF of the cell at these non-standard conditions. And we have two jobs. First of all, we need to find E circle, so E at standard conditions. And then we need to find Q. And along the way, while we're doing that, we'll be able to figure out what the number of electrons is that's transferred. And when we can do that, we can put that in for N. So let's first of all find E circle, E at standard conditions. E at standard conditions, remember, is equal to the cathode minus the anode. And so we need to look at this reaction right here and determine what the half reactions are. And if you look at them, the first reaction that we're going to look at is the Cr2O7 minus, and it goes to, on the right-hand side, our 2 Cr plus 3s. And if you're signing oxidation numbers here, you'll notice that oxygen is minus 2 times 7, so it's negative 14. It's got to add up to be negative 2, and there's 2 of these chromiums, so chromium here must be positive 6. So notice that chromium's gone from plus 6 to plus 3, therefore it is reduced. This is our reduction half reaction, and remember it's red cat, so this is our cathode. This is our cathode reaction that's going on. Red cat, I wrote over there. Okay? The rest of this half reaction also is that you take some of these H pluses, 14 of these H pluses, And if we put the electrons in, there's 6 electrons that are transferred, and then it's going to make 7 waters on this side. Over here you can see the 7 waters written right up here in this reaction. Sometimes when you break them up into half reactions, you can just start with those 2 and then go through and balance it like we've done before, or you can pick and choose some things off here that are going to make it a little easier. In this case, 6I minus goes to 3I2s, and you can see it went from -1 to 0, so it went up in charge. So this is oxidized, and this is going to be the anode. Remember, anox is oxidation, or is our anode for our reaction. Now we got to look these guys up for standard reduction potentials wise, and I'll just give them to you right now. The standard reduction potential for the chromium ion right here, chromium ion, it has a standard reduction potential of 1.33, and the standard reduction potential for the iodine is 0.54. So we take cathode minus anode, and so our E circle for this cell is 1.33 minus 0.54, and when you subtract those in your calculator, you end up with 0.79 volts. So that's the standard reduction potential. That's at standard temperature, and of course when we're in 1 molar solutions, or 1 atmosphere pressure for everything. But now when we're going to dump it into the Nernst equation up here, what we're going to need to know is Q, because we can put the E circle in here, standard conditions, but we also need to know what Q is. And Q, remember, is equal to products divided by reactants to the power of the coefficients. And in this case, it would be Cr positive 3 to the 2nd power times I2, which is a solid, so we're not going to put it in there, times H2O, which is a liquid, so we're not going to put it in there, divided by the reactants, which is Cr2O7, 2 minus to the 1st power, times H plus to the 14th power, times I minus to the 6th power. Wow, a lot of numbers to put in there. And if you look, each one of the concentrations is given to you right up here in the question, and they're listed in order of the reaction. So our dichromate right here would be 2 molar. The H plus is 1 molar. The I minus is 1 molar. And the Cr plus 3 is 1.0 times 10 to the negative 5th. Remember to square that critter right there. So this is easy. 2 times 1 times 1 goes on the bottom, so 2 goes on the bottom. Square this, divide by 2, and we end up with a Q equal to 5 times 10 to the negative 11th. So that's our Q for this reaction. 5 times 10 to the negative 11th. And then we take that number now, and we're going to put it into the actual Nernst equation up here. So we'll take 5 times 10 to the negative 11th and plunk it in for Q. The E circle right here, remember we calculated before, so now our Nernst equation becomes E at non-standard conditions is equal to 0.54 volts minus 0.0592 divided by the number of electrons transferred, which was 6, times the log of 5 times 10 to the negative 11th. Now where did I get that 6? Remember, I got the 6 from the balanced equation right up here. 6 electrons transferred from here over to this side. Whoops, I forgot to put the 6 electrons on this side. But that's the number of electrons transferred. Now if I'm solving this equation, I'll end up taking the log of 5 times 10 to the negative 11th, which turns out to be negative 10.3, and then multiply that by 0.0592 divided by 6 and subtract it from 0.54. And so my EMF of my cell at these non-standard conditions turns out to be 0.79 minus whoops, I put 0.54 in here. I didn't mean to do that. This 0.79 right here. Sorry, 0.79 was the standard reduction potential of the cell at standard condition. 0.79 minus this stuff right here, which turns out to be about 0.1. And so my E at non-standard conditions is 0.89 volts, because this is a negative number right here, and it's a minus number. So 0.79 plus 0.1 is 0.89. So So this minus sign here, this minus sign here, ends up canceling each other out, making a positive. Okay, so that's the use of a Nernst equation. Let's go on to the next page. And in the next page, we've got a picture of an electrochemical cell. And in this one, they're asking the question, if the voltage of the above cell is 0.54 volts at 298 when zinc is equal to 1 molar and the pressure of the hydrogen is 1 atmosphere, what's the concentration of H+? Now, if you remember back to chapter 16, once you know the concentration of H+, there's something that you can find that actually we talk about with acids and bases a lot. If you take the negative log of the H+, what do you have? Well, you have the pH. So this is actually one of the ways, and the primary way, that you make a pH meter, except you take this whole idea and miniaturize it a little bit, and we'll see it again in the second question right after this one. So first step, since we're at some non-standard conditions here, is we're going to have to find out what H+ is in the Nernst equation. And remember, the Nernst equation is E is equal to E circle minus 0.0592, because we're at 298 Kelvin, divided by N, times the log of Q. And the log of Q here would be products divided by reactants. So what's our equation that's going on here? Well, if you look, we've got zinc going to zinc plus 2, and then we've got hydrogen from H plus going to H. So the cell reaction is zinc plus 2 hydrogens goes to zinc positive 2 plus H2. And if we look at this, our Q then would be products, zinc positive 2 times hydrogen, which is a gas, so it will have a pressure, divided by our reactants, which is H+, but remember, you're going to have to square that. And here's a good example of where an equilibrium constant expression, in this case Q, because it's at non-standard conditions, has pressures and concentrations in it at the same time. And it's legal to have those. That's the way that works out. And when you take a further class in this stuff called chemistry, you'll find out that technically they're not using concentrations or pressures. They're using something called activities. But don't worry about that now. It's just that you understand that it's legal to substitute pressures and concentrations together. Remember, Q and K don't have units anyway, so it's good to ignore them. Okay, so the numbers we can put in here now are 1 for the zinc plus 2 and 1 for the H plus 2. Number of electrons transferred, maybe you can see this. There's going to be 2 electrons lost and 2 gained, so there's going to be a 2 in there. In the E circle for the cell, we need to solve for, and to find the E at standard conditions, we'll look up zinc on the periodic tables, the electromotive force list, and we'll look up the standard hydrogen electrode, which maybe you remember is 0. Zinc's is negative 0.76. And so who's smaller? Well, the zinc, so that's going to be oxidized, and the oxygen, the standard hydrogen electrode is going to be our reduction one. So 0 minus a -0.76 is 0.76 volts. So that's our standard EMF. And it tells us that the voltage of the above cell is 0.45 volts. So 0.45 is equal to 0.76. Minus 0.0592 divided by 2 times the log of Q. And let's solve for Q first, and then we can plug it in over here to find out what the H plus is. Okay? So solving for this critter now, we'll subtract 0.76 from both sides. And when we do that, we'll also get these guys over to the other side, and so it turns out that the log of Q ends up equaling 0.76 minus 0.45 volts times 2 divided by 0.0592. And when you take and multiply those guys all together, it turns out to be 10.47. So our log of Q equaling 10.47 now. Q, remember, is equal to this stuff up here. But first we've got to get the the regular log out of the way. So we're going to raise this using the 10 to the x key on our calculator and putting in 10.47. And when you raise that to the power, then Q ends up equaling approximately 3 times 10 to the 10th. Really nice big number. And this is equal to our Q value right up here, which remember is zinc times hydrogen, which is 1, over our H plus squared right here. Okay? So flipping these two from one side to the other and square rooting this thing on this side, we end up with an H plus ion concentration equal to 5.8 times 10 to the negative 6th molar. Now if we wanted to find the pH of this, we could take the negative log of that critter and we'd know. A voltaic cell whose reaction involves H plus can be used to measure H plus or pH. pH meter is a specifically designed voltaic cell with a voltmeter calibrated to read the pH directly and not necessarily the H plus. So here's an example of that. What is the pH of a solution in the cathode compartment of the above cell when the zinc is equal to 0.1 molar and the hydrogen pressure is 1 atmosphere and the cell EMF is 0.542? We're going to do the same kind of problem here again, except this time what we'll do is we're going to solve for the pH. So in this one, we've got E circle, remember from up above, is equal to 0.76 volts. And the Nernst equation says that E at non-standard conditions is equal to E circle minus 0.0592 divided by 2, because there are 2 electrons transferred, times the log of Q. Q, remember, is equal to products divided by reactants, and the thing we're looking for here now is the H plus. So plugging in numbers here, E, it tells us in the problem, is 0.542. E circle is 0.76. 0.0592 divided by 2 times the log of Q. Solving for log of Q, once again, we end up with log of Q equaling 7.3649. I'm just carrying a bunch of decimals along now. And then to get rid of the log, remember we raise it to the 10 to the x on our calculator. And therefore, Q is equal to 2.3166 times 10 to the 7th, a really nice big number. And if we write the expression for Q, Q is equal to zinc positive 2 times the pressure of hydrogen divided by H plus squared, and this is all equal to 2.3166 times 10 to the 7th. And we're told up above in the question that zinc plus 2 is equal to 0.1 and pressure of hydrogen is 1 atmosphere. So this is 0.1 and this is 1, and putting these numbers in and solving for it, this is equal to 0.1 and this is equal to 1, and this of course is H plus squared. Solving now for just the H plus, we'll bring this to this side and this to this side and then square root this side. We end up with H plus equaling 6.57 times 10 to the negative 5th. And if we want to find the pH is equal to the negative log of this critter. And this turns out to be 4.19. So you can use an electrochemical cell that involves the hydrogen ion to find the pH of a solution, and a pH meter is nothing more than a specialized electrochemical cell. Good luck on your non-standard calculations using the Nernst equation and electrochemical cells.